Let's go ahead and get started. I know that people are going to be coming in and out, and you can leave whenever you need to. I had quite a few questions from my students wanting to know how to do titrations and buffers. And so the last 2 years, actually this is 2000. Last year, obviously you got to see the mock exam, which was the international version or the B version. And this is the other version that was administered to our students last year. The good news is, well, I don't know if it was good news, but last year, Avon High School got to see Question number one says a 1.22 gram sample of pure monoprotic acid, HA. Don't get your panties in a bunch over what HA is. It's just a generic acid that has one hydrogen. Was dissolved in distilled water. The HA solution was then titrated, there we go, with a 0.25 molar solution of sodium hydroxide, which is a what? Strong base. So we have a weak acid with a strong base. And for all titrations that we care about, that's how it's going to be. It's going to be a strong base or acid with a weak. All right. As a sidebar, and I don't know if it's going to ask any buffer questions, but what makes up a good buffer, generically speaking? Okay, a salt. I heard a salt. And a weak acid or weak base of that salt. Okay, so no strongs in a buffer, a good buffer. Now we'll add a strong acid or a strong base, and again, a good buffer can handle either of those. All right, and again, a buffer has a small change or resistance and change to the pH. Now there is a limit to that. What's that called? Buffer capacity. So we can exceed that. So hopefully we don't exceed that. All right, so continuing on here to sodium hydroxide, the pH was measured throughout the titration, and the equivalence point was reached at 40 milliliters. That's important. That's not a distractor. The equivalence point was met at 40 milliliters. So if you see something like that, one of the first things I would do is write at equivalence point. Just put it on there. That way you don't have to go back to the question. You don't have to go, I wonder when we hit the equivalence point. At the equivalence point, what does that signifier represent?
Number of moles of H plus moles of OH.
Good. Moles of acid are equal to moles of base. Or the moles of, in this case, the hydrogen ions are equal to the moles of the hydroxide. Okay? Those guys are equal. And it's all about the moles when we're doing titrations. Okay? All right. Let's see. So 40 milliliters of the sodium hydroxide then titrated. The data from the titration are recorded in the table below. Okay, so we have two pieces of information that we don't know about yet. All right, so we do have some information, and obviously when we hit the equivalence point, does that pH make sense? 8.62 makes sense for the information given to us. We have to first of all recognize, does that make sense? Why? Okay, so we start with a weak acid. So if you start with a weak acid, the equivalence point should be on what side of the pH scale? The basic side. If you start with a weak base, the the equivalence point should be on the acidic side. All right, keep that in mind, especially when you're doing titration curves. All right, also when you're doing a titration curve, make sure you know where to start. All right, so letter A, it says, explain how the data in the table above provided evidence that the HA is a weak acid rather than a strong acid. Go ahead. Somebody tell me. Help me out here. Yeah, I'm sorry.
Couldn't we point out that the pH change when on the basic side very quickly at the equivalence point? So
good. That is a really good point. In other words, since we have the equivalence point is on the basic side, and it took about 40 milliliters of our sodium hydroxide. So what I had written down here was 40 milliliters since the pH was above 7 at the equivalence point, and we're using a weak acid. Again, you do not need to write a dissertation. Okay? A good sentence, whenever you see the word explain. Okay? And again, I talked about this to my class. Don't abbreviate, don't use text language, don't use slang, don't say 'cause, okay, or BC because. Now again, you're not going to get counted off for misspelling words or run-on sentences, but use the English language somewhat reasonably well. All right, part B, write the balanced net ionic equation for the reaction that occurs when the solution of the sodium hydroxide is added to the solution of HA. Net ionic equation. Now you guys should be getting pretty good at this. How am I going to start this off? Not everybody at once. Okay, okay, because this is a good question for question. What do we include in the net ionic equation? Let's backtrack. What do we omit from the net ionic equation? Megan?
I said reactants and products.
Eh? Go ahead.
Spectator ions?
Spectator ions. Okay, so we can identify the spectator ions. So here's our generic equation. And again, this would be in your scratch work or in your head. So you have your weak acid with what?
NaOH.
Sodium hydroxide. Okay. And what are we going to form on the product side? Again, this is what's going on in our head or on scratch. NaA, and then water. Okay. Who doesn't change? Or, to better write this, because according to solubility rules, isn't the sodium and the hydroxide dissociated?
But why doesn't HA dissociate?
It's a weak acid. Keep it together. All weaks stay together on the reactant side. Okay? Yes, we are going to take some hydrogens off, but it's not a strong acid. The strong acid, and again, there's always 6 or 7, depending on who you're arguing with. Those are the only ones that dissociate completely. Okay? All the strong bases that we're worrying about do dissociate completely. So on this side, do we have sodium and the anion like this? Is that true? Why? Sodium, good. Okay, and then the water stays together. So how will your net ionic equation look when you finalize this? So HA plus OH makes sodium ions, right? Wait a minute, sorry, nope, sorry. Anions and water. Why does the sodium not show up? It's a spectator. However, we do have the anion over here because it was with somebody. Remember, it's just like when you have your solids and your pure substances. If it's together in a compound or a molecule, when it starts off and then it dissociates and changes into an ion, we do include it. So that's one of the things that I have a battle with a lot of my students, and we did a lot of question 4 stuff this year. But here, the anion is with the hydrogen. Here it is by itself. So the anion is not a spectator, okay? It's a produced ion. So this would be the answer to your part B. Okay. Yes?
Would they ever count us off if we didn't write aqueous below that, or is that just...
Yeah, if you, the aqueous is because of the charges.
Yeah, okay.
Yeah.
Would it be okay, like, if on the answer sheet we had all those other equations but then circled, like, the final one?
Or, I like that, there's nothing wrong with showing your work, but when you get done with it, just draw a line through it, okay? And my recommendation on the free response, use a pen, okay? You're not gonna scribble out like I did, okay? That was stupid, a bad example actually. Okay, so use a pen. It's a lot easier to write with, and if you make a mistake, just draw a line through it. But if you wanna use a pencil, hey, go for it, all right?
Even with a pencil, do the same thing. You make a mistake, instead of trying to erase it and write over it, because it's going to get all smudgy.
Right, don't erase, you're wasting time. Okay, just draw a line through it. All right, part C, calculate the number of moles of HA that were titrated. Okay. How do we start that? What's that? Ooh. Go ahead. Calculate the number of moles of HA that were titrated. Go ahead.
Could we, never mind.
No, we're all here together. Go ahead.
Could we figure out the moles at the equivalence point and maybe subtract it from the total number?
Well, let's start with the first thing you said. Let's start with the moles at the equivalence point, all right? So we need to figure out how many moles we started with. So at the equivalence point, if you know your volume and molarity, what do you start with? Volume, okay? So we've got our 40 milliliters, you can see that. 40 milliliters of your OH, and again, if you need to show this stuff, that's cool. And what was the molarity of our base here? 0.25, right? So 0.25 moles for every liter, okay? And then, what was our ratio from our balanced equation? How much OH did we use with the HA? 1 to 1. Okay, so 1 mole, and this is, sorry, OH up here. 1 mole of OH for 1 mole of HA. Or whatever that equals. It's like 0.01. And do remember, you'll have a calculator for this. Okay. So at the equivalence point. Questions on that?
Bless you.
Okay. Everybody good? Calculate the molar mass of the HA. How would we do that? Look at your information provided there. You already know one part of it, yeah.
You're given how many grams you have it, so you just do grams.
Do grams and then what?
Grams over moles.
Fantastic, good. So molar mass is grams over moles. We just found our moles. Not real happy with the screen. So we have our moles. So you have your 0.010 moles, and what was it, 1.22? Yeah, 1.22. You know, whatever that equals. Like 122? Oh, while we're talking about it. Sig Figs. How many Sig Figs should have been in this answer here? Okay, don't look at my work here, but how many should have been given based on the information provided?
3.
Okay, so we have 3 here, good. And again, and is Blasky still? Oh, there she is. Mrs. Blasky, correct me if I'm wrong, you're given a leeway of 1? Or do you know the official? I've been told that numerous times, but.
I have been told that sometimes, and I've also seen some score sheets where they were looking for very specific things.
Okay.
Those are usually on very simple calculations.
Okay, so, and
They're not
again.
gonna give you any more leeway than 1.
Yeah, they're gonna give you a leeway of +1 or -1, but just to be safe, ask yourself how many Sig Figs are in the question. And we don't look at pH to determine Sig Figs, okay? Because you're always gonna have 2 decimal places. But here there's 3, I'm pointing here. Here there's 3, here there's 3. So I'm willing to bet there should be 3 Sig Figs. Okay. All right, so here we have another equation. Says that the equation for the dissociation of HA and water shown below, where we have this, and you're given a Ka value. E says, assume that the initial concentration of the HA solution before any sodium hydroxide was added is 0.2 molar. And again, we're still playing off of the data from above as well. Determine the pH of the initial HA concentration. Okay. How would we do that? Ice charting, yeah. Okay, so if you're not sure, always think back to ice. So we have our, I need a range here. I can write. Okay. You know my window of, oh my God, that's small. There, that gives me a visual cue. So we have our HA, and if you want to include water, that's fine. You don't need to if you don't want to. Okay, so we have our 0.2, was it? Yeah, so 0.2. How much of the initial do we have of these? 0. Okay, so that goes to X. And again, if you need to show an ice chart, you may. An ice chart will never be graded. Okay, so our expression is the H3O plus, the anion, or the HA, don't include water, ever. Then you have your X. May we use 5% here? Yeah. The only time we wouldn't use 5% is when?
Do we have to have the water on the rapid side?
No. So if you wanted to go just this, that's cool. Okay. What did I ask? Oh, when can you not use the 5% rule? Or when may you not use the 5% rule? Yeah.
When Ka is like a lot less than 1.
Okay. Well, the good news is we won't get one of those. But if you know the pH, in other words, they tell you the pH of the point, or at some point in time. When do we care about the pH? Do we care about it at the initial, the change, or at the end? At the end, okay? So if you're given the pH, it's signifying your concentration at that point, okay? So if you knew your pH, this is your value for X, okay? That's really important. And so whatever this, all that is. Anybody get a number? So, and Ka was equal to what? 6.3 times 10 negative 5. So X squared. So 1.26 times 10 to the, what is that? 5. And then take the square root of that. And as a heads up, probably would not be a bad idea to show all this. Okay. So 3.55 times 10 to the 123. So there's your X. And what was the question asking? For pH. So how do you get pH? Negative log of the hydrogen concentration. Which is like 2.45. Okay. Now you will be given a lot of room. Okay. Don't do what I'm doing here. If I were a grader and I looked at this, I'd take it and throw it away. Okay. So organize your work on that. I apologize. I've got like this much room to work on my Elmo here. Okay. Be prepared to do something like this. Now, Hannah, you were asking about an ice chart. Is this good, or do you want? Well, we could do a titration one. Well, actually, this is getting ready to do titration. All right, and then the last question here: calculate the value of the hydrogen concentration in the solution after 30 milliliters. 30 milliliters. Oh, for this one here. Sorry, this one here. Sodium hydroxide solution is added, and the total volume of the solution is 80 milliliters. Okay. So, how can we go about that? How? What do we know, or what is given from the data? Speak now, don't hold your peace. What's that? Molarity is one of them, okay. For who? Do we know the molarity of the acid? And I would agree, yes, we do know the OH. Do we know the molarity of the acid? So it was given as well. So we know both the molarity of our base and we know the molarity of our acid. Okay. Do we know the volumes of these things? Okay. We know the volume of who? How much is there? And again, it's going to be, and if you don't see a lot of table reading, graph reading, chart reading, I will be surprised. And those of you who took the PSAT, the science section, there was no science in that. It was all reading charts, graphs, and all that crap. And that's the way that the AP exam's headed toward. So be sure that you can interpret data or measurements. All right. So we know that we have 30 grams of the sodium hydroxide. How much of the acid do we have? Stay put. 50, good. And use your information. So you have 80 there and 30 there. Take the difference of the two. Okay. So if we have that information, our hydroxide, again, if you know the volume and the molarity, we have 30 milliliters of our base from our table. And it's a 0.25. And that'll give us our moles. So again, when we're doing titration, let's find out how many moles we have. And then for the hydrogen, don't care about the HA. It could be HA, say that. 50 milliliters. What was it, 0.2? And that is 0.01. Okay. So what do we do with the moles? There's two avenues you could take. I think what I did with my students is I took these and made an ice chart, or actually, yeah, make an ice chart here. So we have our anion plus the water. And if you want to reverse it, that's fine. I just really like having the hydroxide or the hydrogen ions on the product side. That makes for a nice clean Ka or Kb expression. And in this case, what kind of expression could we have? Could have a Kb, but you also could use the Henderson-Hasselbalch equation. Okay, but hey, we're just doing an ice chart right now. So how much anion do we have initially? Small amount, so approximately 0. The water, don't worry about it. And then plug in your values here for the HA. So we have 0.10 moles and 0.0075 moles. Which one's smaller? And don't always go with the hydroxide, okay? Or the strong. So that one goes to 0, and then equilibrium is reestablished. And then we'll subtract it from these. Yeah.
I think it's 0.01.
Point. What's that?
The HA, I think it's 0.01.
0.01? Oh yeah, you're right. Sorry. Sorry guys. So still is the hydroxide smaller? Yeah. And then what is the difference of that? It's a 0.0025. And then on this side we'll add the 0.0075. Okay. Now, did anybody use the Henderson-Hasselbalch? Because I don't think many of my students did. Did anybody? Did you talk about it?
Not for this question.
Okay. Could you use the Henderson-Hasselbalch here?
Mm-hmm.
Why? I see a nod. Don't nod your head and don't confirm. Remember that Henderson-Hasselbalch equation looks like this. Oops, sorry. The negative pKa plus the log of the anion over the HA. Okay, so if you want to use that, then we don't have to use or find a Kb expression. But it is your call. Okay, if you're not comfortable with this, don't use it. All right. However, if you are comfortable, then we have to do a couple things here. What's the first thing we need to do? Probably get these to molarities, right? So if we want to find out the concentration for our anion, what do I do? 0.0075 moles over what? What's my volume here? 80 milliliters, very good. So if you need to do this, that's fine, nothing wrong with that. Or if you can do it in your head, but I'd be willing to bet that a lot of us would do some dumb mistakes when it's crunch time, so probably showing that wouldn't be a bad idea. So 0.09375 molarity for our anion. Another piece of paper down here, just don't get too sloppy. And then the the HA is the 0.0025 moles over the same volume. And so we get 0.03125 molarity. Okay. So we have our HA and our A, or our anion. Morning, Caroline. Yeah, grab that sheet on the corner there. So from this, we already have our expression that we had earlier, which is right here. Okay. And we have our Ka value, which is here, kind of, sort of. So we can plug in our Ka, which again is our anion times our hydrogen. We don't know our hydrogen, so we know, and again that's 6.3 times 10 to the, what the heck was that, -5. So we can plug those in and show that. Okay, and then rearrange. So we can multiply the 0.03125 on both sides, divide the 0.09375 on both sides. Now, the worst part about this is just remembering what to do, right, Hannah?
Yeah.
What are the chances, if I were a betting man, that you're going to see a titration? I'd say probably 45% chance. Okay. And then betting for a buffer, I'd say 45% chance. Betting for a KSP, 10%. Okay, if I added those up right. Now, I will give you a heads up, if you see a lot of acid and base questions in the multiple choice, it might be your lucky day and you might have a KSP for question 1. Anybody get a number for the hydrogen? 2.1 times 10 to the -5. Okay. And that's what the question was asking. It wasn't asking for the pH, right? Calculate the value of the OH. I'm sorry, the hydrogen. Any questions about anything that was done here other than from anyone other than Caroline? Okay. I would anticipate if you were to work a problem out like this, that of the 55 minutes, it may take you 20. Okay. If you were to sit through it, think about it. Okay. Also, remember, unfortunately, there weren't any questions on this question here, okay, that we could not use a calculator. Well, there's a couple, but those were really easy. If you get to a question where you have to write something out, and we're in questions 1, 2, or 3, I would skip it and move on to the calculator portion, because when you finish with 4, 5, and 6, you can come back to 1, 2, and 3. You just can't pull your calculator out. Okay, so think about that while you're working these out. Be smart, be time efficient. Bring a watch, you can't have your phone out, all that fun stuff. Okay? All right, guys, I'm gonna let you ask some questions to either me or Mrs. Blasky. And then if there aren't any, then we've got another problem on the back there. That's a buffer question. Fire away. Come on, yes.
So what specifically does number of moles of HH titrated mean? Like, what does it mean when that amount of something is titrated? Does that
Okay.
just mean that?
Okay, when we talk about a titration, I think I have a picture of it in here somewhere. Thought I had a picture. Anybody in my class, do you have your acid and base review packet? I don't have it in here. Yeah. Oh, never mind, I found it. My bad. All right. All right, ask your question again.
What exactly does it mean by number of moles titrated?
Okay. When we talk about the number of moles titrated, all right, you're going to have two things. You're going to have something that's in the container. Something in the container could be an Erlenmeyer flask, could be a beaker, could be any kind of container. When we are titrating something, we know the number of moles of the stuff that's in here. And generally speaking, for all the problems that we'll be concerned about, there'll be either a weak acid or a weak base in our container. The number of moles for this doesn't change. Regardless of how much volume of material we add, the moles of the weak acid or the weak whatever, okay, does not change. That's why we always have to find out how many moles we have initially. Now, when we titrate, we're going to have some strong, generally speaking, for all the types of problems that we work, the strong is in the burette. So when we titrate this, we're going to add either, let's pretend that we had the last scenario where this was our weak acid and this is our strong base. We're going to add or titrate our OH to this to kind of balance out the pH or get to the equivalence point. The titrant is in here, and then this is our strong. So I'm not sure if I answered your question. Mrs. Blasky, did you hear his question?
I did not, I apologize.
Ask it again.
I was just wondering what it means when number of moles titrated. Does that mean number of moles added, or not, or something's going on chemically that
Added.
means that it means, okay.
Right.
It's
So
added.
that many moles of the base was added to the titrant. Yeah.
Okay, so we can figure that out by figuring out the number of moles in the equivalence point?
If we know how many moles we have here, then we can determine the equivalence point
Okay.
based on how many moles we need
Oh,
to
I
add.
see.
So
Okay.
when you get into college, you're going to be doing a lot of titrations, especially in organic chem and some inorganic your freshman year. The best thing to do is find out how much or how many moles we have in the container before we start adding, because then we don't have to go drop by drop and go, I wonder if it's going to change. Okay. And knowing the half equivalence point, everybody knows the half equivalence point, right? What does the half equivalence point represent? Blow that up. What is that again? It's your pKa. So if you know your Ka value for your acid, when you start adding and you know, okay, well I know my Ka value. If I take the negative log of my Ka value, the pH will equal the pKa. So I can know, okay, I'm at my halfway point. So whatever that pH is, that volume will be half, should be half. Okay, so if you see this titration curve, say if this is 15 milliliters, where should the equivalence point be at? 30, got it, okay. And then after that, we don't really care because the pH is gonna skyrocket. And what is this a titration curve representing? And let's say that the pH of 7 is, we'll say it's there. I know it's not, but let's say that it is. Is this a weak acid or weak base?
Weak acid.
Weak acid. There's a couple of reasons why. See where we start? Okay, we start on the acidic side of the scale. If it were flipped and say we were doing this, okay, if we had it where we started up here and then came down, then we have a weak base. Now, also some indicators. If your pH is 14, 12, 10, okay, that's also indicative of a weak base that you're starting off with, okay. If it starts up here in the 14 range or 13 range and then drops down to like the 1 or whatever, then you got a strong with a strong. That would be more of a multiple choice type question. It wouldn't be a question that would be asked on question 1, unfortunately. Those are the fun ones. And if you have a strong with a strong, what's the equivalence point? 7. Okay. But with a weak, we'll never hit whether it's a base or an acid, we won't hit 7. Okay. What else? what does this diagram represent for? The titration curve for, again, it could be a multiple choice question. I doubt if you're going to see it on questions 1, 2, or 3. Polyprotic, very good. So in other words, we have more than one hydrogen. Okay. So just know that, okay, we're going to have 2 hydrogens that dissociate from this. This could represent for sulfuric acid. Again, we have a release of our first hydrogen, which is very strong, and then the second one's a little tougher to get off. All right, what else? And we don't have to do just acids and bases here.
Mr. Frank?
Yes.
So when we're looking at the graph and we're trying to decide if it's a weak acid
Okay.
or a strong base, how do we determine
Let me throw. All right. Now ask your question again.
when we're looking at this, how do we decide if it's a weak acid or a strong base?
Okay. If it's a weak acid, then the pH will start typically above 2 or 3 initially. But it won't be like above 7. Obviously, if it starts up here, then that's a weak base. Okay, so if it's a strong acid, it has to be really low, close to 0, in the 1, no higher than 1.5 for it to be strong. And then we hit our equivalence point, and then, now take a look at this one. This one actually is shows how we actually have a weak here. So it's above 2, kind of and it looks different. Notice how the strong kind of curves this way, where the weak is like, little jump, and then the equivalence point. There isn't much of a gap here. There's a big gap here. Okay. So those are some indicators. What else? Doing all right, Carolyn? You weren't up late last night, were you?
No, but my brother